Hi, welcome to week one or lab one of the online regression course that Greg and I are teaching. This video in particular has been re-recorded for the online audience. The original recording was too specific to the offline course with a lot of questions and discussions that may not be useful for people outside that course. One disadvantage of doing it this way is that I don't have an audience to stop me to say, you need to explain that better. I did not understand this, moving too quickly, something's not showing up. Hopefully I don't run into those problems or too many of them, but if you find that some of them are concerning, please feel free to write to me and I'll try and either re-record this session or try and add clarification somewhere. So any kind of feedback would be useful. I also assume you've watched the introduction video that Greg has recorded, that I have recorded. One of those videos are going to walk you through what the lab files are, where to find them, and most importantly, like how to go about creating the class data set that we are using here. It is a publicly available data set that we can't distribute, but you can download and process through a series of steps so that you can get started. We'll first look at an old portion of the original recording where Greg walks through the class data set that we'll be using, which is the EGLS-K, or the Early Childhood Longitudinal Study Kindergarten Cohort, and then we'll come back into the do files to get started.
They're wonderful data sets. They're big samples, they're representative samples. They cover a lot of different kinds of domains that are of interest for education researchers. So we decided to use one of those for the class data set. And we chose one of the kindergarten cohorts, the Early Childhood Longitudinal Study kindergarten cohort. This one began in 1998 and followed kids through 8th grade. There's another one that started up in 2011 that's still going on. You know, you've got thousands of kids who were drawn to be representative of kindergartners all around the country. And they have been followed systematically. The parents have been interviewed. So there's a lot of parent information. The teachers have been interviewed. So the teachers are reporting about the kids. And then the kids themselves take various assessments. So, you know, all the kind of domains of skills and behaviors that you might want measures of, executive function, math, reading, antisocial behavior, all those things are measured persistently across middle childhood, across elementary school. You can do school level analyses. You know, they have a lot. They do principal interviews also. It's just a wonderful general resource for educational research. And what we've done is to take a subset of variables in this ECLS-K 1998 cohort, and to illustrate the kind of things that you can do with it. Why don't you share the screen, Paul, if you've got that up and running?
Yeah.
Oh, okay. I was thinking about the, we can do this. That's okay. Yeah, just go to this one. So this kind of outlines when they measure different kinds of things. This is for the class data set. Or is this for the general ECLS-K, Paul?
This is for the class data set, but I think it's also general. So, but these numbers will correspond to the class data set.
Okay. And, you know, to make things manageable for the class, we've subsetted the variables a lot. But what's nice is that if you have ambitions to take what you might have done for a class project and make it into a research paper, and you want to pull variables in the big data set that aren't in the small data set that you'll be using for the class, that's easy to do because you can merge those variables in based on the ID numbers of the kids. So, it's very useful in and of itself for the exercises you'll be doing, but it's also a very useful general research tool that might be of interest. And what's nice now, the fact there's a second longitudinal study also beginning in kindergarten that began in 2010, 2011, you can look at comparisons between cohorts of kids who were entering school back around 2000 and kids entering school about 12 years later in 2011 or so. So very similar structure to this two different surveys, but what we have is for the original longitudinal study. And you can see children are assessed a really nice, comprehensive math, reading. It eventually, there's some science scores you can get. Fall of kindergarten, spring of kindergarten, right? So you can look at changes over the kindergarten year. For some kids, a 1/3 subsample, you've got fall of grade 1, so you can look at summer reading loss or summer math loss between the spring of kindergarten and the fall of first grade. Spring of first grade, they interview everyone. 3rd grade, 5th grade, 8th grade, right? So it's the same kids being given comparable kind of assessments. And you have, variables about the child, variables about the parents, variables about the teachers and teacher reports of kids. So for behavior problems, for example, the kind of standard assessment of internalizing and externalizing behavior problems, there's both a parent report and a teacher report across all these waves. So, it just serves a variety of research interests, and our problem sets will cover, a small fraction of the kind of information that's available. One of the readings that you'll have either for this coming week or the week after is Fryer and Levitt, which is about achievement test score gaps across different groups. That's drawn from this data set. So it's a very widely used, very nice data set. So enjoy. And as you start to get into this data set, think big, because if you really want to come up with an ambitious paper based on this data set or the full set of variables that are available for this data set, and maybe make it comparable to see what's changed over the last 12 years. All those things are not easily done. It takes a little bit of work to get in these data sets, but it's very feasible to think about a project using these data sets. And what you'll be learning from Paul across the problem sets, are all of the data management and statistical skills that you need to do a really good research paper based on this data set and ones like it. So enjoy the exercises. It's nice to know the kind of numbers that you're calculating are the numbers that are true for the nation as a whole, because these kids are drawn from kindergartens all over the country and designed to be representative of kids around the country. So let me stop there and turn it over to Paul.
Okay, now that you have a basic understanding of the class data set, we're gonna jump right in. Lab 1 is intended to try and give you an understanding of do files, how to write them, how to document them, how to explore the data to get a quick sense of some patterns that you're interested in, and doing some basic cleaning so that your rough descriptive look is not entirely leading you astray, and the beginning of some basic analysis. One thing to keep in mind as you write a do file is that it should be well documented. You want to make it friendly to yourself, and others that you work with. And there are 3 different ways to document or comment in Stata. That's to use an asterisk, a double backslash, or for any long comments that go across multiple lines, a backslash asterisk with asterisk backslash, sort of like bookends of the comment. I use headers to separate my sections. Like I might have a section on cleaning type X of data, and then type Y of data, and then a section for like running basic descriptives or so forth. It's also a good idea to have multiple do files instead of having everything in one. But for now, as you're sort of learning how to write, having a single do file is much more manageable and easier to work with. But over time, you will get used to like creating multiple do files and running all of them through a do file, but you don't have to worry about that now. Just as a reminder, there's some introductory material that's available from Stata, from UCLA, and many other sources. So you should feel free to look at them if any of this is just like too much. Here is some basics of file and folder management. Wherever you store your files, right, you will want to know like the location because you will have to enter that into Stata. So for mine, all of the data in the output from this lab session is going to be stored, at least for this recording session, in Mac, users, Paul U, Dropbox, regression website. Just note that when I did the original recording, it was saved in a different place. And I think I was using a Windows PC to run it, so the conventions change a little bit, but worry not. It's not a big difference. So I need to first find where I am, and if you type pwd, which stands for print working directory, it tells you the current location that Stata thinks you're in. And right now, it happens to be in the right place where all of my data file are. But if it wasn't, you would just change your directory or change your working directory to the folder location that you want to be in. And if you like hit ls, I never understood what it stood for. In my mind, it's just like listing stuff. It tells you what's in that folder. And so since you're in the right folder, you can just load the data like this. Now, getting this address right can be tricky in the very beginning. So if you're not sure like how to type out the address, one easy way is to just do a drag and drop. Let's start with a different file. So it's, wow, let's just put this in. You can put it into the command prompt window, and it will give you the address and the file, right? You can also just drag it into the, I don't know what this is called, but like the results window, and it will give you that address and file name. So you can copy paste this portion, right? When you do change directory, then load the file, or as was done by Stata automatically, you can just do it all in one line where you say use this file in this location. You'll notice that there are quotations here. That's because like if you have a space in the folder name, let's say it was instead of regression underscore website, it was regression space website, then without these quotations, you're going to run into an error. And so just use quotations. Sometimes the working directory changes. It makes things easier. It's sort of not what like a normal programmer would do, but this is how a lot of Stata coding handles directories with spaces in them. But this can get like really long to type out multiple times, right? Like this is not a nice thing to have to type out or copy paste. So you can clean this up further by using what's called globals. Globals are stand-in for whatever you want, right? Let's say I use the command global and I call something project to be the stand-in for this long text. Okay. Then the way to use that global, right, which is some sort of like a placeholder, you can say, like, you can now refer to it as project, but with a $sign in front to indicate that this is a global. So if I say display, which, you know, how display typically works, if I say display 1, it'll show you 1. Display 2, I can say display text, right? And it'll show these things. And a lot of text requires quotations because it doesn't understand spacing very well without it. If I say display text 1, text 2, that can be problematic, right? If I say display $sign project, the global that I have just defined, it'll know to print this, because this $sign project is a stand-in for this string of text. Okay. And globals are nice because you can overlay globals, like combine globals. Like if, let's say, you like working with subfolders and you can have, say, like a project folder, and the project folder is named regression website. We have another folder that you built that Stata is not going to make, although you can make a directory with mkdir command, but just, you know, like you make a subfolder, right? And you want to put stuff in there, or you want a global that refers to this, but you don't want to type this out again. You can say global, let's say, call it data, push in this global, and make sure to add the squigglies around it. Otherwise, it'll think that there's a global called project data. If you separate it out with these squiggly brackets, it'll know that there is one global here, and then there's something that follows, right? So if I were to type this out long, this is going to be global project, right, plus what comes after. And you can check by saying, let's set the global called data, right? And let's display data, $sign, to see what this is a stand-in for. But put quotations around it, because what we're going to try and print into the results window is like a long string of text with spaces in between. Right? It printed users Paul U Dropbox regression website data, which is what we would have expected. You don't need to do this. Like, you can also just do this, right, instead. But I'm just trying to show you that you can overlay globals, because globals can be combined. If, let's say, one global is like one text, another global is another text, you can combine those texts by combining the globals. And globals can be whatever you want, right? Like global X, if I display it, again, it doesn't know, it's not going to display it because it's a long series of text. It requires quotation marks, right? I explain what the cap does later, so don't worry about it. In short, it allows you to run a do file even after, like, you run into an error. It's designed to try and capture the error code, which is in this case like 111. But anyways, don't worry about that now. All of this to sort of say, this is one way to manage your files that you are like importing into Stata and exporting out of Stata. But if this is too hard, don't worry. Like, you can simply, as you saw, just drag and drop, right? And say, use this, and then maybe like change the directory at some point. So everything is happening inside the folder, the folder that you assign. Okay. For us, we can now use the data global to load in our data. And so let's try and get a feel for what's inside. Okay. Often the information about your data lives in a different document, but the data itself can tell you a lot. But when I say like a different document, I mean like the PowerPoint slide that has been shared with you that gives you a summary of what variables are in there, how they have been labeled and such. But oftentimes it's like hundreds of pages that document your data. Okay, but let's see what we can learn from just the data itself. If we run describe, and this is short for describe, it'll show you how many observations there are, meaning how many rows of data you have, how many variables you have, or how many columns of variables that you have. A variable, for every variable, its name, the storage type. So str8 here means it's string, but a particular type of string, this is longer than like str4, which is just a shorter string. The display format, don't worry about this for now. Value labels, again, don't worry about this for now. And the variable label. So child ID variable is the child identification number. And you can look through. Another way to sort of get a sense for what's in your data, right, is to run codebook compact. It's a heavier command. It takes longer to run. And depending on how you're accessing data, sometimes it will crash. So if it doesn't work for you, just don't use it. You could just use codebook, which has a longer output, but is less likely to crash for some reason. It tells you like the variable label, like as in describe, and again, like number of observations of non-missing values, how many unique values there are, what the mean value is, what the min value is, what the max value is. And the reason why all of these are blank is because if you recall, child ID was a string and not a numeric variable. So it doesn't know how to create statistics from like text information. What's important about looking at this here is you want to know like what every row represents. Does every row represent a child? Does every row represent a child's particular year? You know, maybe like we have one row for child 1 in grade 1, or age 1, and then a child 1 at age 2, where every row is not really at the child level, is how we would call it, but at the child age level or the child grade level. But looking at the codebook, you can kind of get a sense, right? Because you have 21,409 rows and 21,409 unique values, right? That means every child, right, or every row has a different ID. Like if we browse child ID, none of these are duplicates. And this is one good way to sort of get a feel for like at what level your data are in. You might have some duplicate records, but we know now that every row is a child. So let's look further. You'll see that there's like SID, which is the school ID, and there's numbers 1, 2, 3, 4, 5, 6, 7, and you sort of see these numbers reoccur here, and here, right? Like 2, 3, 4, 5, 6, 7, 8, and 9. So this one is different, but like here's 4. We see it here, T2, T4, T5, A2, A5, and you can look across. Sometimes the variable labels have some information. Nope, it doesn't have the information here. Sorry. Okay. Okay. Describe is useful because Codebook is also like a way to get a summary of your variables. And like described, it will show you the variable names and the variable labels, but it'll give you some additional information. Like it'll tell you the number of observations it has, meaning the number of rows. And you might be wondering, like, why do these numbers look different? It's because it's telling you the number of non-missing values. Right? So some of the rows, if it's missing, like here, it's just going to have a smaller number of observations. There's just no information, even though it's coming from the same matrix of data. What's also useful is like how many unique values there are. If you know that there are 21,409 rows and 21,409 unique values, that means every row has a unique ID, right? In other data sets, you might end up with a child for every row being like a child age level, which means maybe row 1 is child A at age 1, and row 2 is child A at age 2, and then child A at age 3, right? And this is what we would call like a child age level data, but we know that's not the case here, right? Other kind of useful information is like the min and the max value. You have like negative values, and often that's a sign that something odd is going on. And a lot of programming conventions for people who create data sets, they either use for missing data or like maybe someone, like if it's a survey data, somebody refused to answer the question, or they just skipped the question, or for whatever reason it's missing, but you want to like note that it's missing, and it's a different kind of missing. They use negative numbers. Like let's look at like child's composite date of birth month. There's no -9 value that correspond to a month. And it should tell you like, that's probably missing data that needs to be cleaned. Another convention that gets used by a lot of programmers is to use a very large number. Like you might have, again, date of birth month and a value like 9,999. Those very large values or odd negative values are often used to sort of signify that there are missing values for you to clean. You should also get in the habit of like browsing the data. This is sort of like what you would see in an Excel spreadsheet, every row being a child, every column being a variable. You'll notice that these are in red text, and red text means that they are strings or characters. Like if you look here, right, there are like, this is alphanumeric, there's a C here. And here you'll notice this is entirely numeric, but people like to use string values for IDs because numerically 0003 and just 3 are equivalent. And you might want to store the leading zeros. And sort of an easy way to do that is to just convert it into string and make sure the leading values are retained. If we scroll to look at other variables, you'll see that it's blue. Sometimes it'll just be black. And the difference is that these blue values, which I'll explain later, are the numeric variables that have values that have been labeled. But let's not worry about that for now. Okay. So one last way to sort of review what's in your data set, right, would be summary. And it gives you similar information like codebook, right? It gives you the variable name, the number of observations, the means, the standard deviation, min and the max. Codebook didn't give you standard deviation, but I guess the summary doesn't give you labels. But if you notice, it runs much more quickly. This runs much more slowly. And as your data get larger, codebook compact becomes like a difficult thing to run. It takes up too much time. This is why you have variations like describe, browse, or summary to get at the summary that you need more efficiently. Okay. And now let's take a look at the like a selective view. You can say browse and specify the variables that you want to look at: child ID, parent ID, gender, race, WKSESL, WKSESQ5. You don't know what those things are yet, but it's some kind of a number: WKSESL, WKSESQ5, and it's just more specific ways of like picking out the variables that you want to look at. I don't know if it sorts. Okay, so it sorts. If you click on this, it sorts by the variables that have been selected. So you can look at the labels, right? The WKSESL is the continuous, whatever WK means, continuous SES measure. And this one is the categorical SES measure, right? Somebody's in the 5th quintile, 3rd quintile, 4th quintile. Continuous version is some numeric form, which is hard to understand and by itself doesn't have a lot of meaning, and is sort of a useful relative metric that the ECHOS-K developers have constructed. It's a combination of parental education, income, and occupation, and maybe a few other things, I'm not sure, but those are the main 3 ingredients. And we'll be looking more at this later. You can also just, depending on like which system you're using, you could be using Linux to run Stata, and so you don't have this browsing option. You can list out the same kind of information. You say list, add your variable list, and if you say in 1 through 5, it'll mean from records 1 through 5. So this is equivalent to these 5 rows, right? You can tell ID 1, 2, 3, 4, 5. You can say, give me 1 through 6, 1 through 7, right? Or like 2 to 7. But nowadays, you can usually browse things. Sometimes I also have to work on Linux, and so I will be using list options also. There are more things you can do with lists, but let's not worry about that for now. You can also organize the variable further if you want, right? If we're looking at a browsed list, and you might want to sort by gender and then by race. For example, where is gender? Right. So it does all the not ascertained, -9, all the male records, and then the female records. If you say sort gender and race, it'll first sort on gender, right? And so now within male, it'll sort by race, like white, male whites, male black, male Hispanic, male Asian, and then female, more than one race, female whites, and so forth. If you wanted to do like a reverse ordering, so the default sorting is to go sequentially, like 1, 2, 3, 4, 5, but you might want to go 5, 4, 3, 2, 1. Then you say G sort instead of sort and put a negative sign, and it'll know to put then female on top because female has the larger numeric value. Yeah. You can also order your variables so that it appears in the sequence that you want. You can say like order, I want all the child and parent ID first, then I want to see gender, then race, then SES variables. Then that's what you will see. You can order a variable to come after something. So like, let's say this quartile version of SES, you want to move it down, like move it so it appears after race. Then you can do this, and now it's right after race. If you want to look at more options for order and for any variables, you can use the help command, help and write the Stata command. And it'll tell you like if you want an order of ordering such that the variable appears after or before and so forth. Okay. All right. So a lot of mechanics and we'll start exploring the data. But more basics of like looking around the data. This is not too many variables considering like a large data set, but it's still a lot to look through. You might have something like 3,000 variables or 30,000 variables, and this just becomes too hard to like browse through. Then you can do use the look for command. And what it will do is it'll look for the word math in the variable name and the variable label. And anything that matches case non-sensitive, it'll show up here, which is sort of like a descriptive output. And like we can tell, like there are like math scale scores here. So you might be wondering, like, are there any other tests? It's likely to have the word score in it. So let's look for score. And you can see that there's a reading test, a math test, a science test, and we have all of these labels. C1, C2, C3, C5, C6, C7. And we've seen this before. And let me pause. Okay. And if you now look at sort of the summary documentation of the ECHLS-K, if you recall, child assessments all start with C, right? C here for all these like tests. Then 1 refers to fall of kindergarten. 2 refers to spring of kindergarten. 3, fall of grade 1. 5 to grade 3, spring. Notice that the numbers don't line up. 6 for grade 5, 7 for grade 8. So this is just ordered to give you a sense of time, but you have to map it onto something like this to know what C7 or C5 is going to mean. But we know that there are tests. We know that there are multiple tests. And we might want to know, like, what else might be measured at this age, right? At C7, which is child assessment at spring grade 8. So what else might be collected at grade 8? We look for C7 measures, at least in our class data set, and there are more in the full data set, like locus of control, self-concepts. You might want to look at other grades. And what's nice about look for is if you list out two text, like, or 2 search words, it'll always mean C7 or C6. So all the C6 stuff here, all the C7 stuff here, and maybe like C5, to sort of get a sense for what's happening at time period 5, which is grade 3. So grade 3, 5, and 8 are C5, or 5, 6, and 7. These are the kind of assessments that's being done to the child. Yeah. Okay, so that's sort of a general way of like getting familiar with the data. Okay, so now we're going to work on exploring the data. Okay, we'll start with one of the outcome measures here. Often are like test scores. Just a reminder: C1 means child assessment at fall of kindergarten. So the variable we'll start with is this C1 R4 RSCL, which probably stands for, well, C1 being fall of kindergarten, reading. Not sure what the 4 is, but R is for reading. SCL is probably for scale. So let's summarize this variable as we've seen before. And we know that something's off here, so we need to work on cleaning that. We can create a histogram to visually see what the distribution of the test scores are. And that's kind of like missing data of -9, right, is showing up here. Another way to sort of like summarize the distribution is through k-density. Is just like a histogram, just using a much more granular level to sort of show the distribution instead of using bins that take a range of test scores. Okay. And you've already sort of noticed what's odd here. So we'll use an if statement to examine test scores, right? There are many values of test scores, and we don't want to be looking through all of them. We just want to tabulate them if they are less than 0, if they are negative test scores. And we get this output. It tells you they're like values that are not ascertained or not applicable, right? But we don't know what numeric values these are. So we'll tabulate it, comma, no lab, which tells you, and anything that follows a comma is an option that goes with this data command at the very front. So say print the tabs or the tabulations, but don't print any labels, because these numbers or these values can also be labeled, which I think we cover later. But they're -9 and -1, right? This, right? -9 and -1 probably showed up here. And this is what that is. We can also run codebook. Same thing with the if statement. Give me a codebook summary, not compact, which tells you numerically -9 is not ascertainable, -1 is not applicable. Okay. And -9 is sort of a convention that the Eccles K developers use. It can be anything, right? Like some people use -9,999 or just positive 9,999. They just use different conventions to give you, to tell you that something is missing here and you need to be aware of them. But for Stata, it doesn't understand that -9 is a convention for missing, and you have to tell it in the Stata language that it is missing data you don't want to be part of your summary, right? Because it's going to move the mean and then the standard deviation. So you can recode it by saying replace, right? Replace this variable or values of this variable to equal period or dot if it has a negative value, right? So these -1s and -9s, make them into a dot. And let's see it happen. Like let's browse. Right? And so now I should have shown you before, but like this might have said -9, now it's a dot. And Stata understands that dot means missing data. So if we summarize it, you'll see that there are 17,000 records with non-missing values. If we scroll up, it's gone now, but like if you had summarized it prior to this replacing, then this would have been a higher number because -9 would have counted as a non-missing value. So we can try and like revert the process. So replace this variable equals -9 if this variable is equal to missing. Changes have been made, and we can browse. We can browse this variable again, and this -9 is here, right? If we summarize that same variable, there are 21,000 of them, right? But if you convert it into missing, then you have less non-missing values. And this is very important because handling missing data incorrectly leads you to very bad results often. And so, okay, now we sort of know like how to identify missing data, how to deal with them. And the simplest way to deal with them for now is to just give it a missing value that Stata understands, a dot. But there are other ways which we will cover. I think had maybe intended to cover, but we don't cover it here. But it requires like imputations that you don't have to worry about right now. Okay, so here's the summary again, and let's say you want to know the summary for every like subgroup that you're interested in. Here's gender. We'll do codebook, gender. There's some missing values there. 1 means male, 2 means female, right? Just to repeat, these are values and value labels. This is a variable and a variable label. So like you can label these numbers. Okay? So say you summarize it for all the male. So using an if statement, if gender is equal to 1 or male, summarize the test score. And the average score is 34 point something. Let's do the same thing for girls. And they have a higher score, 35 point something. Okay. You can also sort the data right, on gender. And as we have seen, it's going to sort the data and group the gender. So you can say by gender. So it's going to take segments of your rows, right? It's going to take this group and then summarize this variable. And then it's going to go to the next group, male, all the way down and further down, and summarize this variable, then to female and so forth. So we sort the data and by gender, we summarize it. So for group, one group, another group, it summarizes things. Okay. You can do this in one step by sort. Gives you the same result, just less lines of code. Another way to do it is to use the tabulations that we've been doing, right? 13 not ascertained, 10,000 and so forth. And then summarize them. It'll print the mean, the standard deviation, and the frequency. But something I want you to notice here is like this value and this value is not the same. So why does this tabulation tell you there are 10,950 male, and this tabulation tells you there are 8,980 male, or like male students? Right? And it's something to like think about, like why is that happening? It's not lining up, and that's because some students, right, don't have a math score. So let's do just a summary of the math test. There are 17,000, right, non-missing values, and then say, and then there are like more than 20,000 records with gender data. And so when you do something like this, it's only going to be able to summarize the test scores for people who had non-missing values for test scores. And so the ends here don't match the ends here because these ends or these records have non-missing values on test scores. We can recreate this frequency table if we say, let's tab the genders, let's tab gender. If they are not missing, exclamation means not in programming language, MI for missing. So if they are not missing test scores, what's the gender count? And now it looks like what we saw before. Right? The ends now line up. Okay. Let's now introduce another grouping variable. Here's, like gender, but also SES quintiles that we saw before. Right? Categorical SES measure. Let's tabulate them. We know that some of them have like truly missing values in the Stata language, right? And it, and now it shows up here because this is a missing value, and tabulate comma M will show this missing value. There are 13 of them that line up on this category. Children who are not ascertained, also don't have, for whom we don't have like children who have a non-ascertained gender value are also, like 13 of them are also missing the SES measure. 666 children who are male are also missing SES measures and so forth. Okay. And so don't forget about the missing, we got to recode them. But we'll recode them later. But for now, let's get a better understanding of these statistics, right? This is one way to compare like how many male students are in the first quintile and female, but sometimes you want percentages, right? Comparing these numbers is not as easy. So you can do tab comma row, which gives you row percentages so that these, right, or these percentages sum to 100, right? So it's 1,944 divided by 3,770, that's 51%. You can get column percentages, right, where the percentages here sum to 1 going down the columns. You can also do like cell percentages, where if you add up all of the percentages here, then that's 100%. So 2,133 divided by 20,141 is 10.59%. Okay. You can also try and look at everything. And there's a legend here. It says like first printing frequency, row percentages, column percentages, cell percentages, but it's often too much, so people don't really use this. Okay. And again, we'll just summarize the outcome by using another grouping variable here, SES quintile. So we know from first quintile to the fifth quintile what the average kindergarten fall reading test score looks like. And the higher SES students have a higher test score, which is something you might expect. But it's not so easy to visualize, as the number of numbers that you have to look at like grow. So you can try and graph it, maybe create a bar graph bar, right? And it's not terrible, but the like the labels are overlapping, but you can at least get a sense that this is the first one. Likely this is the fifth quintile, and that the scores go up. And but like you can try and flip it, make it a horizontal bar, so you can sort of see it better, and you can visually see that scores are higher for higher SES kids. But if you and bars are useful for comparing means, but how do you compare distributions visually? You can use like a box and whisker plot, which is graph box, and you can sort of see this. But it's not as helpful. It's a bit scrunched. You can sort of see that the distributions look different, but it's not so helpful. So we can use like a two-way graphing where you can graph multiple things. So like we'll do a K density plot that we've done before, right? And you have seen this, but then by the quintile levels of SES. And this is one way. It's a little bit better, but still it's hard to see the differences, right? It's produced 5 different plots. But maybe you can like, but maybe there are different ways. Like we can try and get a more detailed summary, right? Of where the percentiles are. And the way to read this is here is the mean. At the 50th percentile or the median, that's what the test score is. At the first percentile, that's what this score is. And then it repeats for like 75th percentile, 99th percentile, what the 5 smallest values are, right? This being the smallest, what the 5 largest values are, this being the largest. Okay. And maybe what we want to do is sort of get rid of the outliers, not because that's always a good idea, but like just so that we can look at the distributions and not be worried about like here, like or this figure where the longer tail makes it hard for us to see what the main distribution or where most of the distribution is. Yeah. So when we run this summary, right? Let's cut it off at the 91st percentile. Like, so we'll only look at all the kids all the way up to the 95th percentile, and we can use an if statement. So run K density, right, for the same group disaggregation by SES quintile, but only if they are scores less than 50.54, which is the 95th percentile. And now we sort of get a better picture of how the distribution compares and not just how the means compare, right? Like the first quintile is sort of skewed so that it peaks less at the center and more on the lower score. And then the higher quintiles have a more normal distribution, but it feels like the mounds at the top of the mounds are moving kind of to the right, right? Where on the top SES quintile, there's like more of the kids are closer to the ceiling than they are at sort of the like at the mean values within that grouping. And we can now try and limit this now by other groups like race and ethnicity. There are some missing values here that we'll have to deal with, but let's say we want to look at the distribution, right? This same kind of distribution here, this graph that we saw before when race is equal to 1, or for white students, or race is equal to 2 for Black students. And if we run this, right, it's running the K-density plot for the test scores if they're less than 50.54 and their race is equal to 1, right? So the distribution across the quintiles for white students, and then here for Black students. And maybe there are like some differences, but it's hard to compare the two because the plots are disappearing. So how do you get the graphs to like not disappear? And to do that, you have to give the name. Like we're going to call this in one of the options of 2A, right? We're going to say name math underscore W, and then math underscore B, W for white, B for Black. And comma replace means when you graph this with the name math underscore W, replace it. So it means overwrite it. Like, let's say we didn't have this and we run 2A. Now we have a figure called math underscore W. If I try to run this again, it will tell me it already exists and it doesn't want to get rid of it without my permission. And so if I say comma, replace, it means overwrite it, right? So math W now becomes whatever this is. And so it'll just repeat itself. And now we can have two graphs that we can go like toggle back and forth with to say like what does the distribution look like by SES for white students and for Black students. And you can see like it's not a perfect comparison because the Y scale is a little bit different, but something where I got kind of stuck was the Y values are not the same here. And the Y value here is going to be like the density, like not the same, but something like the proportion of people. And I want them on the same scale so I can compare graphs. And so what I added here as an option is I said for the Y label, right? Show me from 0 to 0.1 and in units of 0.02. So that way, if I create one for the white sample, for the Black sample, they're on the same scale now. So visually, I can compare them. So if I go from white to Black or from Black to white, you can sort of tell that you can compare the distributions better. And sort of get a sense for like whether the distributions are very different, whether the height of the distributions are a little bit different by quintiles. But there are, of course, more formal ways of testing this, but this is sort of a quick visual look. And now let's say you want to save the graph, then you can say graph save, and math B is this graph, right? The distribution of test scores by quintile for Black students. You have to call this name and then save it as a separate file by saying save it to output. And if you recall, output for me is my project folder and the subfolder output. On my computer, that is this folder, my project folder and output. So it'll save there this math file. And I can go and look at it if I want by opening it up, and it'll be the same graph. Okay. So save them, and you can overlap them instead, right? Instead of having one for every figure, you might want to have in the same figure multiple lines, right, to sort of get a better visual look at the mean or the variation. And then we're going to stop with the stated figures here because it's like endless. Sorry, just one more. What if you wanted to sort of see how the test scores have changed over time for this cohort by SES level? Right? Like we could run codebook for all of this, and now it's going to look a little strange. Like, what is that asterisk doing here? If you recall, we started on this variable, right? We know that we want to look at reading scores, and that there are lots of reading scores. So you like look for reading, and what I'm looking for is a pattern in the variable name, right? Let's limit it down to our scale. Look for our scale, right? Is that they look very similar, except now C1, C2, C3, C4, C5, C6, C7 are what's different about the variable name. And I could like look for our scale within the variable window here, copy this and say codebook compact and get the summary that I want. But I can also make use of the fact that the variable names look similar by using an asterisk. Asterisk just means any character or any characters. So these are variables that start with C, have something in between. In this case, it's 1 through 7, right? And end with R4 RSCL. And that's what this is doing, right? It's sort of a way to clean up your codes or like use the nature of your variable names in a way that makes your code more efficient. Let's say I want to look at, for all of this summary statistic, but divide it up by the quintiles, right? Like give me the summary for every quintile. You can use tabstat or like tabulate statistics to say, and let's just run this and see what the default gives you. It gives you for every variable, right? C1 to C7 reading scores, the mean value, 35, 44, 51, 75, 125, 149, 169. The Eccles K is not vertically aligned or had issues with vertical alignment. But I think right now, I think it's trying to be vertically aligned. There are problems with this, and there are references that talk about the limitations from this, but you can kind of, let's assume they're vertically aligned, and an average kindergartner knows less than an average 8th grader. Just a reminder, C7 is 8th grade spring. Okay. You can also get tabstat to give you the same kind of information, but then disaggregated by the SES quintiles. So now this is the mean value of all the students in the first quintile for their C1, fall of kindergarten, spring of kindergarten, C3, I think is fall of first grade, and spring of first grade, and C5, which I think is spring of 3rd grade, spring of 5th grade, and then spring of 8th grade. But now maybe you want like more numbers, right? You might want to like know like what's the n size for every cell, the mean, which is presented, standard deviation, the min and the max, and you can tell tabstat to give you more of that information. But this is like hard to visualize, right? And so we can try and do a simple quick copy paste to get an easy visual of these numbers with Excel. Okay, so I'll pause and do that real quick. Okay, so we're gonna go back to this output, which just has the means. And while you can follow these numbers, it's easier if you can visualize it. So if you can copy this, so highlight it, say copy table, which is important. It means it'll copy the matrix with the sort of the divisions of the numbers into a matrix. Go to Excel and just paste it. Sorry, let me do that again. Copy table, paste it. You don't need this information. You can move this over, right? Make it a little bit more compact. And the total is here, right? And you just want to take a look. So say insert, recommend, no, let's not do that. Let's do a line graph. And very quickly, you can sort of get a sense for what's happening over time, right? The first, on the very bottom is the first quintile. On the very top in light blue is the fifth quintile. And you can tell that over time for the same group of students by SES, the test score gap is increasing over time. All right, this here we saw a gap of maybe about like, that's 41, that's 29. So about like a little over 10. By 8th grade, it's like, here's 186, 145. So like 40 points. It's growing over time. So it's a very quick way. Not the best graphs. You'll have to do some cleaning, but just sometimes it's useful to get a rough sketch, to get a quick pattern without doing too much work. So that's one way. You can also do the same thing by like within 2 levels of groups, right? So this is the tab stat command that we saw here, but we can also do like by sort on race. So that same trend broken it up by race, and then you can try and visualize them if you want. Just telling you that you can like layer different stata commands. Try this quick practice here. I know like the answers are here, but try and find the mean of the first grade reading score for males who lived in Central City. And you might be really confused, like what is Central City? And part of it is like using the tools that we have sort of talked about so far to try and execute this without looking at what's here. Okay. So let's, pause the video if you want. And I'll give you one hint. Central City, right, is a level of urbanicity. Okay, so assuming you've tried it, we got to first find the reading score, and we've seen the reading scores, right? And this one, C3, as we know from our summary, is going to be the first grade reading score, right? This one. And so we can summarize this, but we know that there are negative values, which are missing values that we have to be worried about. Gender, we know male. There are different ways to figure out that male had a value of 1. If you weren't sure how to find information about Central City, you might have looked for urbanicity, right? Or look for a city, but there's nothing there. Then K-urban-R tells you some location type. So you might want to codebook K-urban-R, right? And you'll notice Central City is the K-urban-R with the value of 1. So now what we're going to do is we're going to summarize the reading test score. If gender is equal to 1, and if K-urban_R is equal to 1. But again, there's the missingness, so we have to be worried about that, right? It tells you that the mean is 46, but you know there's some error there. So let's say I'm going to, okay, this is done it. Summarize it only if the value is greater than 0, as in not negative. So more precisely, the mean first grade reading score is 51.15. So we're gonna learn how to do some basic cleaning of the data. These names are not so friendly, so let's give them easier names. We'll use the rename command, which is just rename old name with a new name. And if you're ever unsure about how data command conventions are, you can just say help data command, and it'll say like rename old variable name, new variable name. That's the order in which you do them. Here are some examples, like rename EXP to experience, INC to income, and so forth. Okay, so we're going to rename things for reading 1, and 1 in here is going to refer to the same numbering system, as in 1 is kindergarten spring, 2 is kindergarten, 1 is kindergarten fall, 2 is kindergarten spring, and so forth. So we'll just use those numbers for now and do it for the reading test, the math test, the general knowledge test. Later, we'll learn how to use loops so that the code is not as repetitive, and you can have a shorter, like less lines of code. Okay. We'll also create dummy variables, which are like yes/no variables or 0/1 variables. We know that from gender, like there's this categorical variable, and we want something that says female yes or no, or male yes or no. But we also want to get rid of the negative missing value. And we saw how to do that. Another way to like recode or replace variables is to use the recode command. You say the variable name and say turn -9 into missing. We run this, right? Now it's gone, right? It's not showing up anymore, right? That's those 13 records. It's not like entirely gone. Like you can still say like tab, and it's here. Tab gender, comma M for missing. So you can see those 13 records presented as Stata's understanding of missing. Another way to do this, which we've done before, is to just sort of say replace gender is equal to dot if gender is equal to -9. Something you'll notice is you see 1 equal sign, you see 2 equal signs. When there's 1, you're assigning a value. When there are 2, you're evaluating a value, right? So if this is true, an evaluation statement, you're using double equations, replace gender equals that, it's an assignment value, right? You're assigning a period to gender. Okay. Oh, sorry. Okay, here we are. Okay, and now we're going to try and create a dummy for female. And for this course, we're going to follow variable naming convention by putting a D in front of the description. So D female means a dummy variable for female. We'll start out by creating an empty variable, right? Period. We'll give it a 0 if gender is equal to 1, right? Gender equal to 1 is male. So they get a 0 for female, and gender is equal to 2 is going to get a 1 for female. Right? Another way to read this is 0 means false, 1 means true. And so the dummy convention is that the 1 always describes the dummy variable descriptor. And you should always check that your dummy generation process was done well, right? Like here is the categorical variable, and then the female dummy, right? The 0 lines up with male, 1 lines up with female, and the missing lines up with missing. Now, it doesn't always work, okay? So let's say we drop female, and just a reminder, cap can just be put in front of any regular command line. It'll run even if it errors. So let's say we have dropped female. It's an error. It's not going to work. But if you have capture in front or cap, it'll just ignore it. And if it's not an error, it'll execute the state line. And so what about this? If I generate D female, right? Can I say give D female 0 if gender is equal to 1, right? And give it d female equals to 1 if gender is equal to 1, because after all, right, 2 is greater than 1. But you should check. And you'll notice something odd, right? Previously, this is what you saw. Now, this is the table output. What's missing is there's no missing value for d female. People with the missing value on gender, the 13 of them, now they got a 1 for female. And why is that? Why is that? And it's very important to sort of like realize that for Stata, this missing value, this negative, this period is registered as a very, very, very large number. And so this very large number is greater than 1. I don't know why Stata uses this convention, but because it's very, very large, right? It also got a 1, right? And so it's something to be careful about. So if you were to do this, you would say like replace the female equals missing if gender is missing. Right? That way you have a missing value for d female when you have a missing value for gender. Another way to do this, right, is you might just start with generating d female equals gender is equal to 2. What this means is you can think about it like this. Here's a statement. Gender is equal to 2 could be true, could be false. And so generating a variable based on this statement will give you a 1 when this is true, a 0 when this is false. Okay. Now, how do we know that, right? Like, so gender is equal to 2. This is female, right? They're going to get a 1. When this is false, right? When gender is not equal to 2, which means gender could equal 1, male, or gender could equal missing, we're going to give d female 0, which is why we have the male correctly coded here, but 13 missing, who received a 0 for d female instead of missing. And so we say, we might follow that up with replace d female is equal to period or missing if gender is not equal to 1 or gender is not equal to 2, which is equivalent to sort of saying replace d female is equal to missing if gender is equal to missing, because something that when gender is not equal to 1 or 2, it can only be this. But something went wrong here, right? Something went wrong here. Why? You know, this is the OR operator. And that's because if you do an if statement with OR using missing values, it can be a little bit tricky. Like if it's not equal to 1, that's male, right? So female is not equal to 1. And missing is not equal to 1. So they're going to get a missing. Not equal to 2 means you could be male or missing. And so you're also going to get a missing. So everybody got a missing. This becomes clearer when we realize what I should have used, which is presented here, right, is to use and, like, give d female a missing if, right, gender is not equal to 1 and it's not equal to 2. And that gives us the right, like, code, right? If it's not equal to 1 and it's not equal to 2, then it can only be this, right? If you use an OR statement, then there are lots of possibilities. Both of these are not equal to 1. These two are not equal to 2. So all 3 categories satisfies one of these conditions. So all categories satisfy this long if statement. Anyways, so something to be careful about. And it doesn't matter like which one you use, but it will matter, right, that you check that your categorical code categorical variable lines up with your dummy variable. And in the beginning, it's very easy to confuse the missings and end up with the wrong dummy variable. And as mentioned, we're gonna now learn how to like label the dummies or categorical variables or these numeric variables. So if I say tab, the female, right? They're not labeled. So we don't know what 0 means. We don't know what 1 means. I mean, we typically know as like a programmer what 1 and 0 means, but in some cases you might want to give them labels. And so we'll just use this as an example. You need two static commands. One is label define. The other is label value. This is the convention, but basically you're saying label define, and we're gonna label it something. We're gonna give it a name for this label. Call it dummy. Say 0 is gonna mean no, 1 is gonna mean yes. And this just defines a label identifier, right? Now we have to apply this rule to the female, right? There's nothing in here that tells us that this has modified the female. We just know that if we use this label identifier called like dummy, 0 is going to mean no, 1 is going to mean yes. So say label values, the female dummy, right? Label values, the variable name, and the name of this label identifier. It's now going to update the female. So if I say tab, right, the 0, 1 without labels, and now with labels, I'm missing. Oh, sorry, let me do this again. Right now the 0 and 1 has been labeled. You can check with codebook. You can recycle this, right? Like let's say you wanted to create one for like male. So say like generate the male is equal to, I'm trying to make this bigger, right? Generate the male is equal to missing. Replace the male is equal to 1 if gender is equal to 1. Then if you hit Control R, it'll bring up the previous code. Say give it a 0 if gender is equal to 2, which was for female, right? But and double check that that gender and the female, the dummy has been well coded, and it has. Then we can say like label values, and we're gonna label male with this dummy that we already created. And so if I tab the male, it's now labeled. Of course, we can get rid of the label. So this here is not specific to a variable. This one is. This is why it's sort of in 2 steps. Okay. One thing I want to note is before we talked about describe, and I skipped over this section. Getting long now, but there's this value label column, and that's what we just created. And we just called it dummy. So all of these are value labels that have been defined by someone and applied to the data that you're working with. Okay. A few more practice. I don't know if I did this in the original class, but maybe it's useful to do here. And try and do it on your own. Practice recoding missing for the age variable or R1 underscore K age. This is, I think, age in kindergarten. You'll want to use summary or histogram to find out what the numbers stand for, especially for like missing values. But give it a go or just like continue watching. We can create a clean version of the age variable, and I'll make sure you know how to find it too. If you just look for age, whoa, sorry. Say look for age. There are lots of age, like age at first birth of the current mother, I think, age of the mother, father, and so forth, teacher. This one, composite child assessment. This is probably age of the child in the kindergarten assessment. And I think because it's R1, this is kindergarten assessment fall. So like how old were they in fall of kindergarten? So we'll just replicate, sort of like duplicate the variable, and we'll just give it a new name. we'll summarize it, and you'll know that before you cleaned it, right? Because there are all these like negative numbers. The mean is 65.7. You can also look at the histogram, and there's something odd here, which you know has to be cleaned. So we'll clean it out by assigning it the missing value that Stata understands. And after we sort of clean it, the mean value goes up by 68, up to 68 point something, because it's not being pulled down by the negative numbers anymore. And you can compare how different they look, right? You can compare the n sizes, which are different, and sort of the ranges, which are different. Okay. We'll do a few more practice. Create a dummy for the highest performing 1% on the first grade math score. And think about how you would do that. And here's how you would do them, right? Like we already know which one is the math score. We renamed it as math 3, 3 being the fall of first grade. And we know that there are going to be like missing values to clean up. So we'll do that here. We'll clean up the missing values. And we'll look at it again, and there's still more missing values. This is why it's useful to do something like codebook math 3 if math 3 is less than 0, because equals k uses sort of a negative value for missing conventions. You might be missing some of them, right? So if you didn't know this and you were working on a different outcome, you would do something similar. Right. And so you know that you have to clean up the negative ones. Sure, we can get a summary here. We want an indicator for the students who are in the top 1%. We'll give everybody a 0. We'll make sure people who are missing a math score gets a missing on our dummy because we don't have that information. When we ran the summary, we knew that the 99th percentile is at 88.27. So if your math score is greater than or equal to 88.27, then you get a 1. So we can tab to make sure. And something's odd, right? Something's odd. We have asked for missing, but all of the missing has gone away. And that's because this missing value of a period, right, is considered to be a very, very, very large number. And so when we ran this if statement, it turned all the missing into, so like all the missing values ended up getting a 1, right? And so let's get rid of this. This was not made well. Let's repeat this process, but we can add another condition when we create when we assign a value of 1, that it cannot have a missing value on math 3. We can check, make sure the missings are there. And so we know like things look good, but sort of the missing value problem comes up again and again. We'll create one more variable. We'll clean one more variable for age. As you saw before, we already kind of did clean it, but what do I mean? Let's look at a histogram. It's, somewhere between 55 and 80, but they're not 55 to 80 years old. This is probably in months. So if we want the age in years, we'll just divide by 12, right? And we'll call it age, right? And now we know that they're probably between 4.5 years old to 6.5 year old. You can also run a histogram, and overlay into the options like a normal curve that has the same mean as your histogram, and a k-density plot, which is sort of like a histogram, but you can kind of see how normally distributed the kids are in terms of their age. Oh, sorry. We'll label the variable by saying label var. This is the command. This is the variable that we're naming or labeling, and this is the text that we're labeling it with. Next, we'll review t-test and ANOVAs. just as a reminder, they're both like basic tests to see if you can reject the null hypothesis of group equivalence, meaning like, do two groups or like multiple groups have the same kind of outcome or the same kind of score or characteristic, right? And so a t-test is useful when you have two groups or like comparing numeric values by a binary variable. Or an ANOVA is useful when you have more than two groups or compare numeric variable by a categorical variable with like 3, 4, 5, or whatever categories. So if we wanted to, for example, see if girls on average score differently than boys on first grade math, right? This is a two-sample t-test, right? Comparing two samples. We would say t-test, math 3, the variable of our interest, which we know we've cleaned because there are no negative values, right? By the female, which we know is just the yes, no variable, right? And so, running this produces lots of information, but not to be intimidated. If we tab the female, like we have done before, and summarize math 3, this table is producing similar results, right? Like people in the no group, as in boys, scored 43.5, and the yes group here, which is yes to the female or female girls, right, score 42.9. These are the same numbers, right? And these are the same ends. This here is the combination of them all. Here's the total mean for the entire sample. And this is the difference between the two groups, right, which you didn't get to see. So the t-test output is giving you similar information, just a few more things, right? And it's testing the null hypothesis that the difference is equal to 0, which is another way of saying that the groups are on average equal. And your hypothesis test tells you whether you can reject this null hypothesis. And the p-value for the two-tailed test is here, the 0.1428, that there's, I guess, like a 14% chance that the null hypothesis is true, right? And this is the alternative hypothesis, which is that the difference is not 0, right? And traditionally, you want the p-value to be less than 0.05 so that you can be 95% confident that differences between two groups are like statistically significant or like meaningfully real. So you would interpret this as like girls on average score 0.6 lower than boys on kindergarten math, or I don't know, sorry, this is first grade math in the fall. The difference is not significant, right? The t-statistic is not above the sort of the t-statistic threshold of like 2.9 something. And p-value is larger than 0.05. If you want to know more about t-tests, you can go here. And earlier, we had created like an indicator for who is in the top 1%. And let's say we do a t-test on age, like are the kids who are in the top 1% of the distribution in the math score, and the kids who are in the next 99% different in how old they are. So this t-test is telling you whether kids who are scoring in the top 1% and the kids who are in the next 99%, right, have different ages, and whether that difference is statistically significant. And you want to be careful because there aren't a lot of kids in the top 1%. But so this is really just for demonstration only. And the p-value for that is like less than 0.0001, or like it's about 0.0001. And so you could say that kids who end up in the top 1% tend to be a little bit older. But you want to be careful of this kind of comparison. Anyways, what if you have more than two categories? Then you'll want to run an ANOVA. And we'll use the urbanicity category as a reminder. There were 3: central city, urban fringe, small town, and rural. And ANOVA, right, math 3, which is the variable that you're trying to compare groups on, k-urban, which is the grouping variable, gives you the hypothesis testing result. But this is not as intuitive as using one way, which give you similar results. If you compare the F test, it's the same F statistic, right? But this is easier to read, but it doesn't have the intuitive name of one way. So if you run one way, it'll give you the same tabulations. Like here are the three groups, here are their means, standard deviations, right? This is equivalent to sort of saying tab, k-urban, summarize math 3, right? This is identical. And here is sort of your ANOVA test, are the between group differences. And the null hypothesis here is that for all three groups, the difference among them or between any pair of them is 0. And if you reject it, which is what this is telling you here, that the p-value of that hypothesis test is less than 0.0001, right? That some groups are different from one another, but it doesn't tell you which two groups are different or which two groups might have similar scores on average, right? Because there are three groups. And so a more straightforward kind of way to test group differences is to do pairwise mean on the same math 3 test score over the same urbanicity variable. And there are these other like specifications. You don't have to worry about them. If you look at the results, it's telling you, right? When you compare central city to small town and rural, that difference is 2.95. Oh, sorry. If you're comparing urban fringe and large, compare urban fringe and large towns versus central city, that difference is 2.9. And that difference is statistically significant, right? It has a large t statistic and a very low p-value. If you're comparing small town and rural against central city, that difference is negative 0.3 and not statistically significant. And then this compares small town and rural versus urban fringe, and their difference is statistically significant. You'll learn like to get past this, but this is sort of just an introduction of showing you how to code t-tests and ANOVAs, but all of this will sort of get replaced by regressions, which can generate the same kind of results. Okay. One last practice. Did kids with like no siblings, one sibling, or two siblings differ on their teacher-rated first grade social interaction? So we'll look for sibling. And this is the variable P1 num sibling. We'll tab it, right? And there are 3,000 some kids with 0 siblings, 7,000 some kids with 1 sibling, 4,000 some kids, about 5,000 kids with 2 siblings, right? So let's say we'll generate one, like generate a variable called sib012. We'll give it a 0 when there are 0 siblings, 1 when there's 1 sibling, 2 when there are 2 siblings. Okay. And this is the kind of numbers that we have seen before. Okay. Now for the characteristic measure of our interest, something to do with social, right? It was social interaction, and here we go. Social interaction, P4 in time 4 is spring of grade 1. Okay. We'll do a quick summary. We realize they're missing values, we'll need to clean. We'll generate a new variable this time by so basically duplicating the variable and then replacing it to missing when it's negative. But also like check just in case -9 is not the only, right? In case -9 is not the only missing value, and everything looks fine, right? Okay. Now we'll do one way. What we're trying to see is of these 3 groups, is the social interaction, which you might expect to be different across kids who have siblings or don't, right? Are they different? And they're not, which might be a surprise because you might expect that kids without siblings maybe lack social skills on average or something like that. And at least descriptively, that doesn't necessarily seem to be the case, but there may be other differences that might be explaining the relationship. So this kind of like bivariate relationships are very limited in what it can tell you. Okay. You can also like limit it down to like, what if we like limit it to just girls? What if we limit it to just boys? It seems to be true either way, that you cannot reject the null hypothesis. Anyways, now make sure to save the data set. And you're going to save it into a file called 4ps1. This file will get used for your problem set file. The first week's lab is kind of taxing because there's a lot of like tedious things to get used to. And there's kind of like, they're a little tedious to like talk through, but hopefully they will sort of pay off with, like good returns on your learning. I hope it's useful.